Water harvesting for crop production. Water is the most resource for public health industry. Water harvesting for crop production. Water is the most important resource for public health industry and irrigation. Keeping this in view, a major thrust was given on increasing irrigation potential by undertaking major medium and minor irrigation projects. This led to phenomenal increase in the food production since most of the surface and subsurface water resources have already been developed. Available rainwater needs to be harvested efficiently and utilized to meet ever increasing water requirement for agriculture sector. In order to utilize rainwater efficiently for irrigation, water storage tanks reservoirs need to be properly developed and maintained on the watershed basis, depending on agroclimatic conditions of different regions of the country. Agroclimatic conditions. The harvested water should be properly applied through suitable methods of irrigations to different crops of the regions. Low water requiring crops in particular regions should be selected depending on its agroclimatic conditions. Irrigation scheduling, that is the depth and the time of irrigation during crop growth period, plays an important role in efficient utilization of water, resulting in high irrigation efficiency and an increase in irrigation command and agriculture production. Water harvesting for crop production. Rainwater harvesting for crop production is of utmost importance to meet ever increasing water demand of different crops for enhancing agricultural production. It involves harvesting, storing, and diverting rainwater for irrigation. The harvested water is stored in the ponds, tanks at an appropriate location so that maximum rainwater can be collected from a catchment. Most ponds tanks have their own catchment which provide requisite amount of water during rainy season. Where the catchment areas are too small to yield enough water, water from nearby streams or irrigated canals is diverted to supplement water in the ponds. The harvested water can directly be used for irrigation. It can also augment groundwater storage, which can be pumped through wells during lean periods. Benefits. Rainwater harvesting is beneficial for crop production in following ways: makes provision for collection and storage of water in the close vicinity of the agriculture field for supplemental irrigation during critical period of crop growth. Increase availability of water in the hard rock areas where groundwater is scarce. Makes water available for irrigation of different crops in the areas where groundwater is saline and unusable. It helps in controlling runoff, reducing floods and soil erosion. It also results in enhancing soil moisture for meeting water requirement of crops and increases groundwater recharge as impounding ponds and lake act as the percolation ponds which can subsequently be used for meeting water requirement for crops. And the collection and storage. Rainwater harvesting for crop production involves construction of storage facilities like village tanks, percolation ponds, and on farm water storage ponds and tanks. They arrest and store surface runoff to be used as a source of irrigation water. The stored water can be used for providing supplemental irrigation to the crops. The area to be irrigated depends on the amount of water harvested, storage capacity of the tank, pond, and the water requirement of the crops to be irrigated. Water stored in the storage tanks and lakes is measured by establishing a gauge station. The gauge is nothing but a graduated pole which is marked with the scale following metric system. Total volume can be calculated by multiplying the pond area with that of depth of water, which can be measured from the gauging station. Discharge from the small streams and canals can be measured by different methods. You will be applying quite elaborately the methods to estimate storage capacity of different structures and discharge from surface and groundwater structures in the course on practicals. Water harvesting systems for crop production. Different types of rainwater harvesting system are used in different agroclimatic zones of India based on availability of surface runoff, site conditions, slope and volume of water to be stored for irrigational uses. Different types of structures need to be constructed. Various water harvesting techniques can be grouped into in situ water harvesting techniques and surface water harvesting techniques. In situ water harvesting means harvesting rainwater where it falls in soil profile. Soil and water conservation measures falling under this category include contour bunding, bench terracing, contour trenching, nala bending, and contour vegetative barriers. These techniques help in conserving rainwater during different rainfall events, which can be used by the crops later according to their requirement at various stages of the crop growth. Depending on the amount of rainfall received during a particular season or year, the crop growth and consequently the productivity may vary. The normal rainfall may result in adequate storage, conservation of water, and consequently good crop stand and good yield. In case of below normal rainfall, the water stored in soil profile will be less and hence low yields. In such a situation, an important role is played by the soil conservation techniques to conserve enough water so as to support satisfactory crop growth. Surface water harvesting techniques of rainwater harvesting for crop production include pond, tank, percolation tanks, check dam, nala band, groundwater dams, or subsurface dikes or underground bandaras, nadis, farm ponds, and diversion of stream canal waters to dried up dug wells. Based on the water requirement, availability, and site characteristics, one combination of more than one rainwater harvesting practices is adopted in different agroclimatic zones. The in situ and surface water harvesting structures. Rainwater planning and design of water harvesting structures, pond or tank. Rainwater harvesting techniques that are particularly useful in augmenting the availability of water for crop production in rural areas can be adopted at a moderate cost with the involvement of the local people and locally available raw material. The design and construction of these structures are discussed below. Pond tank. The size of a pond is usually dictated by the availability of adequate land in the vicinity of the village. The size of the pond is based mainly on the water requirement and the catchment area above the pond site from where the monsoon runoff would be available to fill the pond. The following norms can be followed to calculate the water requirement of a village community. Irrigation 600 meter cube of irrigation water for irrigation in a hectare. It is 6 centimeter depth of irrigation. Animal needs are the buffaloes, which is 6 liter per day, dairy cows 70 liter per day, and the sheep 9 liter per day. Storage capacity should be at least double the total water requirement to take care of evaporation and the seepage losses. 10% extra storage may be provided for the sediment deposition. The percolation bunds. The location of bund in the catchment should be such that a small amount of earthwork should provide a large capacity, and capacity should not be too small to be choked up with the sediments very soon. The side should not have excessive seepage losses. Percolation tanks are artificially created surface water bodies submerging a land area with the adequate permeability to facilitate sufficient percolation of impounded surface runoff to recharge the groundwater. These are quite popular in the states of Maharashtra, Andhra Pradesh, Madhya Pradesh, Tamil Nadu, Karnataka, and Gujarat. The percolation tanks have the following characteristics. Percolation tanks shall be constructed in the areas where terrain is highly fractured and weathered. The aquifer to be recharged should have sufficient thickness of permeable zone to absorb recharge. Beneficial area should have sufficient number of wells, hand pumps, etc. The size of the percolation tank is governed more by the percolation capacity of the formation under submergence rather than the yield of catchment. Depending upon the percolation character, the tanks need to be designed. Percolation tanks are normally earthen dams with the masonry structures only for the spillway. Based on the requirement of agriculture development and rainwater harvesting, the country has been demarcated into 16 regions. The recommended water harvesting structures for these regions are as follows. Humid northwestern Himalayas. In the hilly regions of J&K, Himachal Pradesh, and Uttaranchal, following water harvesting measures are recommended. Diversion of perennial springs and streams water in storage ponds or tanks, village ponds, collection from hill slopes, Himalaya foothills in the regions covering foothill areas of the Jammu Kashmir, Himachal Pradesh, and Punjab and Uttaranchal. Sub-Himalayan region of the West Bengal, Assam and Arunachal Pradesh. The recommended structures are the collection from hill slopes, village ponds, contour dredging. Humid and high rainfall northeastern zone in the high rainfall areas of Sikkim, Darjeeling Hills, Arunachal Pradesh, Meghalaya, Nagaland and Manipur, Tripura, Mizoram, Assam and Jalpaiguri and the Cook Bihar with high surface runoff, diversion of perennial springs and streams and storage structures like ponds and tanks are the most important rainwater harvesting structures. And we have the humid Assam Bengal plains. Following water harvesting structures are recommended in the regions covering parts of the lower Gangetic plains comprising alluvium with diverse mix of sand, silt and clay in parts of West Bengal and Assam. Tanks, check dams, contour bunding, subhumid and humid Satluj Ganga alluvial zones. The region cover parts of the Punjab, Haryana, UP and Bihar. Eastern part of this zone receives very good rainfall and western part faces drought-like conditions at few places. The recommended water harvesting measures for this region are ponds and the check dams. Northwestern semi-arid and arid zone. Rainwater harvesting measures recommended for the zone in western Rajasthan are the gully plugging, nadi, talab, khadin, or the percolation tanks, gully plugging, contour bunding. Central semi-arid Vidhyana zone. Water harvesting structures in the zone comprising of southeastern district of Rajasthan, southern district of UP and central parts of MP having very low irrigation cropping intensities are the ponds, check dams, contour bunding, gully plugging, subsurface dikes. High rainfall, high runoff, Chota Nagpur Plateau. This region characterized by the soils of medium to shallow depth and undulating topography falls in the Jharkhand state and adjoining hilly areas of Bihar. The recommended water harvesting structure in these zones are the tanks, ponds, check dams, anicuts, gully plugging, contour bunding. The Malwa Plateau and Narmada Basin. Water harvesting measures in the region covering major part of peninsular India with an annual rainfall of about 900 mm are ponds, check dams, subsurface dams. South Central Deccan Plateau Zone in the semi-arid region covering parts of Andhra Pradesh, Tamil Nadu, Karnataka and Maharashtra. The recommended water harvesting structures are ponds, check dams, percolation tanks, bandaras, gully plugging, subsurface dams, contour bunding. Chhattisgarh Plateau Zone. The rainwater harvesting structures in the region covering Chhattisgarh state and the southern Ossia Hills are almost similar to South Central Deccan Plateau Zone. The southeastern brown red soil zone, the traditional ponds, tanks, subsurface dams are the structures recommended for water harvesting in the region covering Panchmalai and Kadavur hills and Prairie plain areas of Tamil Nadu and Valley Gond hills and the part of the plains. Southern variable rainfall mixed soil zone. Following water harvesting structures are recommended in the region covering certain parts of Maharashtra and the west central parts of Tamil Nadu with highly variable rainfall distribution. Ponds, tanks, kunta, nadi, check dams, percolation tanks, subsurface dam, gully plugging. South by model rainfall zone. The following water harvesting structures are recommended in this region, covering the southern parts of Kerala, Karnataka, and Tamil Nadu. Ponds, tanks, percolation tanks, check dams, gully plugging, contour binding. Eastern Coromandel. Following water harvesting structures are recommended in the region, covering entire coastal belt of the AP, Orissa, and West Bengal. Ponds, tanks, Kunta, Nidi, check dams, percolation tanks, subsurface dams. Western Malabar. The recommended water harvesting structures in the region covering the western Malabar and coastal areas of the southern Karnataka are the ponds, tanks, kunta, check dams, bandaras, percolation tanks, subsurface dams, contour bunding. A utilization of harvested water. It is essential to maintain optimum soil moisture in the soil for favorable plant growth. Thus, the optimum moisture in the soil is essential for healthy plant growth. Depth of irrigation of a particular crop depends on the water requirement during different crop growth stages. Number and length of crop growth stages vary from crop to crop, and therefore total growth periods are different from different crops. The irrigation should be applied at identified growth stages so as to obtain optimum crop yields. For example, seven main critical growth phonological stages of wheat are identified, such as crown root, initiation stage, tillering stage, jointing stage, flowering stage, milking, and the dough and the maturity. Some growth stages are the more critical than the others, and therefore, depending on the amount of available harvested water, irrigation should not be missed at the most critical stages. First is the irrigation scheduling. Irrigation scheduling helps in deciding as to when and how much water to apply to a field in order to maximize irrigation efficiencies by applying the exact amount of water needed to replenish the soil moisture to the desired level. Irrigation scheduling not only saves water and energy but enhances crop productivity. Irrigation scheduling criteria is based on the soil moisture content and soil moisture retention. The quantity of water to be applied depends on the irrigator's strategy. For example, the irrigator can replenish the soil moisture to field capacity or apply less. If no rain is expected and the irrigator wishes to stretch the time between irrigation, it is advantageous to refill the soil profile to field capacity. If rain is expected, it may be wise not to fill the soil profile to field capacity but leave some room for rain. Proper irrigation scheduling enables the farmer to apply the exact amount of water to achieve higher irrigation efficiency. The accurate measurement of the volume of the water applied or the depth of application is very crucial. The discharge measurement has been dealt with adequate detail in course 4 pertaining to practicals. Irrigation scheduling offers following advantages: enable the farmer to schedule water rotation among the various fields to minimize crop water stress and maximize yields. Reduce the farmer's cost of water and labor through fewer irrigations, thereby making maximum use of soil moisture storage. Reduces fertilizer cost by holding surface runoff and deep percolation leaching to minimum. Increases net returns by increasing crop yields and crop quality, and results in the additional returns by using the saved water to irrigate non-cash crops that otherwise would not be irrigated during water short periods. Uniform water distribution across the field is important to derive the maximum benefits from irrigation scheduling and management. Accurate water application prevents over or under irrigation. The amount of water required for irrigation can be defined in terms of duty and the delta. Duty represents the irrigating capacity of a unit of water. It is a relation between the area irrigated and the quantity of irrigation water required during the entire period of growth of that crop. Delta is the total depth of water required by a crop during the entire period. The crop is in the field and is noted by, for example, a crop requires about 9 watering at an interval of 20 days and the water depth of 10 centimeter in every watering. Considering the crop period of 6 months, the total water requirement, that is delta of that crop, is 9 into 10, 90 centimeters, 0.90 meter. Methods of irrigation. Irrigation is an artificial application of water to the soil to enable crops to have favorable growth, particularly in the areas where amount of rainfall is not adequate. Methods of irrigation not adequate and it is not uniformly distributed. These three basic types of irrigation methods generally used are the surface irrigation, sprinkler irrigation, and the micro drip irrigation, depending on the type of crop, soil, and topographic and the climatic condition. An irrigation method should suit the local conditions. All methods have their advantages and disadvantages. The basic purpose of irrigation is to apply irrigation water uniformly so that each plant gets the desired quantity of water, neither too much or not too little. The suitability of the various irrigation method, that is surface, sprinkler, or drip irrigation, depends mainly on the following: the soil type, crop topography, climatic conditions, source of water and its quality, power availability, and cost and benefits. Surface irrigation. In surface irrigation system, water moves over the across the land by simple gravity flow in order to wet it and inflate into the soil. Historically, this has been the most common method of irrigating agricultural land due to its simplicity and less cost involved. On loam or clay soils, all three irrigation methods can be used, but surface irrigation is more commonly found. Clay soils with low infiltration rates are ideally suited to surface irrigation. All soil types except coarse sand with an infiltration rate of more than 30 mm per hour can be used for surface irrigation. If the infiltration rate is higher than 30 millimeter per hour, sprinkler or drip irrigation should be used. Surface irrigation includes the following types: continuous flood or paddy irrigation, in which small basins are flooded during the growing season. Basin irrigation confines water by ponding over the area. In orchards, a separate basin is formed for each tree and water is supplied through a supply ditch. A border strip irrigation applies water to one end of a rectangular strip of sloping land so that the water advances down slope and either runs off the end or ponds behind a dike. The border strip method, wherein the farm is divided into a series of strips 5 to 10 meter wide, are commonly used for all close growing crops, including cereal crops like wheat. Furrow irrigation uses furrows made between crops planted in rows to control the guide water for either steep land or very level land. This method of irrigation is commonly used for row crops like the maize, jowar, sugarcane, cotton, tobacco, and groundnut, where water levels from the irrigation source permit. The levels are controlled by the dikes, usually plugged by soil. This is often seen in the terraced rice fields where the method is used to flood or control the level of water in each distinct field. In some cases, the water is pumped or lifted by human or animal power to the level of the land. Advantages like the simple, cheap, and easy to operate, suited to the most of the close growing and the row crops, and adopted for most of the soils. Limitations: irrigation efficiency ratio of water gainfully used by the crop and water applied from the source is very low, as a result of which scarce and the precious water resource is wasted. A considerable area used by the water channels, periodic maintenance required, and leaching of fertilizer and the nutrients. Sprinkler irrigation. Sandy soils have a low water storage capacity and a high infiltration rate. They therefore need frequent but small irrigation applications. In particular, when the sandy soil is also shallow, under these circumstances, sprinkler irrigation is more suitable than surface irrigation. The sprinklers operate at a considerably higher pressure of 2 to 3 kg per centimeter square. The sprinklers apply water in the form of rainwater, which helps in the creating better microclimate and also protect plant from frost. The system is suited under following soil, crop topographic, and climatic condition. Sandy soils with high infiltration rate, undiluting topography, close growing crops, moderate wind speed. Sprinkler irrigation systems are divided based on whether the structure moves in the field during the irrigation event. There are four basic categories. Permanent solid set sprinklers are fixed on the risers from buried lines or lines suspended above a crop or over trees. Hand move sprinklers are fixed sprinklers that are disassembled, moved, and reassembled between irrigations. Continuous move sprinkler systems move continuously during irrigation. Center pivot irrigation systems supply water at a central point and a lateral line rotates around this center and cover very areas at a time. Advantages: uniform water application as per the requirements in the field, improves microclimate, high irrigation efficiency 70 to 80, high fertilizer efficiency. Limitations: high initial investments and operating costs, needs high energy. High wind velocity affects uniformity of water application. Drip irrigation. In drip irrigation, also known as the trickle irrigation, water is delivered at or near the root zone of plants, drop by drop under low pressure. The system comprises of the plastic components such as pipes and drippers in addition to filter and fertilizer applicator. This method can be the most water efficient method of irrigation if managed properly, since evaporation runoff are minimized. In this method, fertilizer is applied with drip irrigation known as fertigation. If a drip system is operated for too long of a duration or if the delivery rate is too high, it may result in a deep percolation. As water is applied in vicinity of the plants, only a part of the area is wetted. As a result of this, there is a considerable saving of water. The fertilizer application is also highly efficient due to its use the irrigation water. Due to optimum use of water and nutrients, not only crop productivity is high, its quality is also superior as compared with surface irrigated crops. The drip method is suited under following conditions: widely spaced crops such as orchard crops, undulating lands with the high infiltration rates, widely spaced crops, saline irrigation water, Advantages are the considerable saving of water is only part of the area wetted, less amount of fertilizer used, relatively saline water usable, high irrigation efficiency, high fertilizer efficiency, high yields, and better quality of produce, less weed infestation, limitations, high initial investment. Water is the most important resource for public health, industry, and irrigation. Most of the surface and subsurface water resources have already been exploited. Therefore, it is absolutely essential that available rainwater is harvesting and stored efficiently to the supplement the ever increasing need of agriculture sector. There is ample scope of harnessing rainwater during monsoon season that receives nearly 80% of annual rainfall. The water harvested and stored during monsoon season can be utilized during non-monsoon period of irrigation. The rainwater can also be conserved in the situ during monsoon period by undertaking various soil and water conservation measures depending on agroclimatic conditions of the region. The conserved soil moisture can be used beneficially for crop production. In order to utilize harvested rainwater efficiently for irrigation, water storage tanks or reservoirs should be properly developed and maintained depending on agroclimatic conditions of different regions of the country. The efficient on-farm water management practices such as proper irrigation scheduling and appropriate methods of irrigation water applications depending on the soil, crop topography and climatic condition of the regions needed to be used to derive maximum advantage of the harvested rainwater. Proper irrigation scheduling not only saves a lot of water and nutrients but also results in the enhanced crop productivity. Selection of an appropriate method of irrigation is crucial in order to achieve high water productivity as well as increasing irrigation command. Several factors such as soil type, crop topography, climatic conditions, source of water and its quality, power availability, costs and benefits influence the selection of the surface sprinkler and drip methods of irrigation. Based in coromandel cropping intensity, crown root initiation stage, delta, dough stage, duty, flowering stage, in situ, irrigation efficiency, irrigation intensity, irrigation scheduling, jointing stage, maturity stage, milking stage, percolation ponds, permeability, permeable zone, ponded water, recharge sediment deposition, and the tillering stage. These are all the keywords of the water harvesting of the crop production or the water harvesting techniques.